Hi everyone, this is the second part of the second lecture of the Biofuels module, the journal club on this article entitled Production of Liquid Biofuels from Renewable Resources. We are going to look at some examples of biofuels and the ways that they are produced in this part of the lecture. So we start off with bioethanol, which we've mentioned previously can be combined and blended with petrol or even burned in its pure form within modified spark ignition engines. Those are the flex fuel vehicles that we mentioned earlier. However, a liter of ethanol contains only about 2/3 of the amount of energy that you get in a liter of petrol, and so if you're filling up with ethanol alone, that means you'll be filling up more regularly. Ethanol has a higher octane level than petrol though, so when it is mixed with petrol it actually improves performance, and this is important because it improves petrol combustion in engines and therefore reduces the emissions of carbon monoxide that we see, as well as unburned hydrocarbons and carcinogens. So adding ethanol in your petrol, even at a 10% mixture, will have some improved greenhouse gas emissions advantages. Crops such as sugarcane, wheat, and maize are resources that are most often exploited for bioethanol production at the moment. Bioethanol is the most highly produced biofuel in the world, and it is done mainly still in this first generation method of using either sugar from sugarcane or starch from maize. Compared with corn and beet sugar based ethanol, the sugarcane based ethanol has considerably more favorable energy balances and a reduced greenhouse gas emission. So what do we mean with energy balance? We mean that with producing any fuel, especially a biofuel, there's a lot of energy input. If you're growing a crop to produce a fuel, you are spending a lot of energy maybe planting plants, maybe for spraying plants, for harvesting plants. All of that requires a lot of energy being burned. And then you finally make a fuel product. And so what we mean with energy balance is when we compare how much energy we put into making this fuel with how much energy is inherent in the fuel itself, do we actually produce a product that has more energy than what we've put in? And when it comes to corn ethanol in the US, the energy balance is actually very thin. They only produce slightly more energy than what they're actually putting into making it. When you're using sugarcane, though, the balance is about 1:3, so that's a far more favorable energy balance. And when we move to second generation biofuel, it's been calculated that you can get positive energy balances of 1:8. So let's look then at this lignocellulosic biomass, sometimes called cellulosic ethanol or lignocellulosic ethanol or second generation ethanol. This is where we use plant biomass and the sugars inherent in that plant biomass in order to make ethanol. Now that plant biomass or lignocellulose, it mainly consists of cellulose microfibrils that are embedded in lignin, hemicellulose and pectin, with varying amounts of each compound depending on the plant species. So not all plants have the exact same amount of cellulose, hemicellulose or lignin, but they all vary with the plant species that we're talking about. So here we have our cellulose microfibrils. This, as we mentioned, is essentially glucose chains that form these fibrils. They exclude water, and so we talk about a crystalline form of cellulose. Interweaved in this is hemicellulose, which interact non-covalently with cellulose and covalently with lignin. Lignin is a polyphenol, and all of these together gives us this structural strength of the plant cell wall that the plant needs to survive. So for the plant, this is not a food source, it is a structural component. So cellulose, as we said, is a crystalline glucose polymer. It's a homopolymer, consists only of glucose. Hemicellulose is much more variable. It's more amorphous, so it's not as tightly packed in a crystalline structure. It consists mainly of xylose and arabinose, again, depending on the plant species, and there are some other pentose and hexose sugars there as well, whereas lignin is a large polyaromatic compound. We can't break lignin down to a fermentable sugar. We have to do something else with it. Now, in order to turn lignocellulose into ethanol, there are many steps, and we did mention that there are some thermochemical methods as well, but looking specifically now at the biological steps, there are 3 general steps for producing lignocellulosic ethanol. First is you require a pre-treatment of your substrate. So your plant biomass doesn't go into the process as is. It has to be size reduced. We have to grind and chip it down to small size. And then we require some kind of pre-treatment. And we'll speak a little bit more about pre-treatments later on. Essentially, this is a chemical or physical process that we use to swell those cellulose and hemicellulose fibers so that it can let water in and let enzymes work more effectively. Then we have the enzyme step. We add enzymes to our lignocellulosic fibers, and we get a saccharification process, that is the release of fermentable sugars from those sugar polysaccharides. And then you have, of course, a fermentation process where your sugars that have been released from the polymers get fermented, and then the back end is the distillation to separate your ethanol, and you can use the ethanol exactly the same way as you would to the distillation, and the final cleanup processes of ethanol is exactly the same in first and second generation ethanol production. Now, there are many different ways of combining this enzyme treatment with the saccharification treatment, with the fermentation, that will go into more detail later on in the course. We can do this process completely separately. So your enzymes are produced separately, and then you sacharify your feedstocks separately from the fermentation, or there are various ways of combining the saccharification and fermentation steps that we will discuss in greater detail further on in the course. So comparing this with our starch to ethanol process a little bit earlier on, you'll see it's a little bit more intensive. You need also size reduction to start off with. You make a slurry by mixing it with water, and then you do some kind of pre-treatment. The example here is called steam explosion. These pre-treatments use much higher temperatures than you needed with the liquefaction of starches. Then you cool the mixture, and you allow the enzymes, the celluloses, to saccharify for the saccharification of your sugar polymers, mainly your cellulose here, because the pre-treatment methods quite often are very good at disrupting the hemicellulose already. So it's mainly the cellulose that still has to be saccharified here. And then you add your yeast, and we have a fermentation process similar to what you had for the first generation ethanol production. The difference here would be that your substrate loading is lower. We can't quite mix this plant biomass as well as we could the starch sugars or the free sugars, and so therefore you don't have quite as high ethanol production level in this tank over here during your fermentation process. And that does make the distillation a little bit more expensive, a little bit more difficult to do, but essentially distillation and dehydration and fuel blending, the back end of the process is the same for both first and second generation ethanol production. So as I mentioned, we need this pre-treatment process in order for the process to work more efficiently. Pre-treatment is designed to facilitate the separation of cellulose, hemicellulose, and lignin. Those 3 main polymers of lignocellulosic biomass. And we need them separated so that the carbohydrate polymers can be more easily broken down by enzymes into their constituent simple sugars, and those simple sugars can then be fermented. So the aim of pre-treatment is to remove most of your lignin and hemicellulose from the cellulose, reduce the cellulose crystallinity and increase the porosity of the material overall. And that allows water to get in there, and that allows improved hydrolysis. So there are different pretreatment options, and in later journal clubs we'll talk about this again. Just some examples for now. We have steam explosion that I've already mentioned. We have ammonia fiber explosion. We have carbon dioxide explosion. These are explosion methods are essentially the material is put under pressure, and then that pressure is released very quickly. If you're thinking Michael Bay type of movie explosion, this is not it. But that rapid decompression opens up the fiber of the lignocellulosic material quite effectively. There are also other methods such as ozone treatment to degrade lignin, acid hydrolysis, where you can use higher concentrations of acids to almost completely hydrolyze the polymers, as well as ionic liquids. All of these methods have some advantages and disadvantages, and unfortunately there's no optimized process that works for all types of feedstocks. Whatever your source of your lignocellulosic is, if it's a different type of agricultural waste or hardwood or softwood, you have to optimize specifically for your feedstock, as all of these feedstocks, as I mentioned, are slightly different in their combination of how much cellulose versus hemicellulose versus lignin they have. The other unfortunate part is that the pretreatment methods always release some fermentation inhibitors into your fermentation broth as well. So we get the release of weak acids such as acetic acid. We get furfurols, which are breakdown products of the sugar itself. So glucose will be released, and then some percentage of that glucose in the mixture will be further degraded into something like hydroxymethyl furfurol, which is very toxic to some fermentation organisms. And then you get phenolics that are released from the lignin. These can be quite toxic in the mix as well. But pretty much every pretreatment method that you choose will release some fermentation inhibitors. It's just inherent to the process. So after the pretreatment for the lignocellulosic ethanol process, we said that we have these enzymatic processes to completely release the fermentable sugars, the monomeric sugars, from the cellulose and hemicellulose. So we're looking at cellulose here. And I'll remind you, it's a crystalline polymer of long chains of glucose, and just a simplified way of showing it, these lines would be your glucose chains, and they stack together mostly in this crystalline form. Every now and again there's a kind of less ordered part which we call amorphous cellulose. And because of this crystalline structure, it's quite difficult to depolymerize or break down, and that's why we will also see lignocellulose or cellulose specifically being referred to as a recalcitrant substrate. So it is depolymerized by combinations of enzymes, and these combinations of enzymes are called cellulases, and there's three main types of cellulases. The first is called endoglucanases, that's drawn over there, and what that does is it specifically attacks the cellulose in these amorphous areas. So endoglucanases attacks in that regions of low crystallinity, and that creates more free ends. And the free ends are important because the most important enzyme in breaking down crystalline cellulose is the cellulobiohydrolase. So it's a type of exoglucanase, which means it binds to a free end, and then it processes along that glucose chain. It basically peels it off of the crystal and releases cellobios in the process. So it degrades the molecule further by removing cellobiose units from the free chain ends. So we need endoglucanases to create more free chain ends, and then very importantly we need cellulobiohydrolases to be able to actually degrade the crystalline parts, and it removes cellobiose, which is essentially two glucose residues held together by a beta-1,4 bond. And then the final enzyme is beta-glucosidases, and that is the enzyme that hydrolyzes that cellobiose that is released by the cellulobiohydrolases in order to give us that free glucose that can then be fermented by your fermentation organism of choice. And so once the polymer structure has been broken down, the constituent glucose is simply fermented to ethanol by most often yeast or bacteria. The industrial standard is to use the yeast Saccharomyces cerevisiae. Hemicellulose, as I said, this is different from cellulose in that it is not crystalline. It also contains different types of sugars. It's not a homopolymer. It contains mainly pentose sugars such as xylose and arabinose, although there are different types of sugars in different types of hemicelluloses. And for complete enzymatic degradation of these substrates, you actually require many more enzymes than the three types of enzymes we just discussed for cellulose. Although, as I also mentioned, mostly the pre-treatment processes are harsh enough to break down a lot of the bonds in hemicellulose already. So the fermentation process of hemicellulose is more difficult though, because you have these 5-carbon sugars and they are more difficult to efficiently ferment than the 6-carbon sugars like glucose. Lignin, the other polymer that, as I said, consists of phenols. It is not, you can't break it down to sugars because it's not consistent of sugars, so it's not fermentable, but it can be recovered and utilized as a fuel in terms of you can dry it and burn it, and that can provide some process heat and electricity. More recently, people are trying to do better with lignin in terms of extracting antioxidants that can be added to foods. They are trying to produce certain gums or glues even, which are slightly more highly valuable products than burning it. The old adage was you can make anything you want with lignin except money, but there seems to be some ways these days of using lignin a little bit more efficiently than just burning it. So there are still lots of gaps to fill in. As I mentioned, we need improvement across the entire value chain, and this is certainly true for lignocellulosic ethanol at every step. So some factors that are intensively researched to improve the economic conversion of biomass to ethanol include the development of more efficient pre-treatment technologies. As I mentioned, these basically have to be optimized in every process depending on the feedstock that you use. We want to try and minimize cellulase inhibition. If you are using a separate hydrolysis and fermentation process, it means you're trying to hydrolyze all of your cellulose first before you start the fermentation step. And as you hydrolyze more of your cellulose, you get more free sugars being released. And we quite often with most of these enzymes, there's a simple feedback inhibition loop where the more free glucose there is, the worse your beta-glucosidase, for instance, works. So we're trying to select enzymes or mutate enzymes so that we can get rid of this feedback inhibition. There's investigation of different process configurations. As I said, we'll speak more about this in the rest of the course. Whether you completely separately hydrolyze your feedstock and ferment it, and this process is called separate hydrolysis and fermentation, or right at the other end of the spectrum would be consolidated bioprocessing, where you have one microorganism that basically produces the enzymes to release the sugars from the lignocellulosic material and then ferments them to a product that you actually want. And there are various combinations that can be done, which we call different process configurations, and we still require optimization of those as well. We could also enable cellulolytic ability in bacteria, yeast, and fungi, and in plants to create entirely new cellulase production systems. And this might be either to reduce the cost of actual production of these cellulase enzymes, or for what I've mentioned, that consolidated bioprocessing, this direct microbial conversion of the substrate to a product of interest. We also need to enable xylose assimilation in our most efficient fermentative organisms. So that would be the bacteria Zymomonas mobilis and the yeast Saccharomyces cerevisiae. They are very, very good fermenters in turning glucose into ethanol, but neither of them naturally use xylose as a carbon substrate. So through genetic engineering, people have enabled them both to use xylose at relatively good rates. And then finally, how to integrate all of the different components into an economic overall process into an economic production system of ethanol. So still a lot of research work that's being done. An alternative to ethanol for a fuel is butanol. Butanol is a 4-carbon alcohol, and it contains more heat energy, and it's easier to blend with gasoline than other hydrocarbon products and other hydrocarbon products. So because you can more simply blend it into petrol, gasoline, it is considered a drop-in fuel, is what they call it. And you can make a mix of 85% butanol with petrol and use it in unmodified petrol engines, and it still works fine. So butanol is also less corrosive and a cleaner burning than ethanol, and can be distributed through existing pipelines, which you'll remember is one of the problems with ethanol. You can't pump ethanol through existing fuel pipelines because it mixes with water. You have to do ethanol blending at the point of distribution. Butanol, you avoid that problem. N-butanol can be produced by anaerobic fermentation of carbohydrates through a bacteria called Clostridium acetobacillicum. And it produces butanol, but it actually produces 3 products called acetone, butanol, and ethanol, which is why it is called ABE fermentation. And you get a product ratio of 3 to 6 to 1 for your acetone, your butanol, and your ethanol. The disadvantages of using butanol is that N-butanol is actually toxic, and it inhibits the growth of the bacteria that produces it, and you only get accumulation of about 12 grams per liter of your butanol formed. So this low product yield is a big disadvantage to producing butanol. We consider that with yeast, you can get well over 100 grams per liter ethanol being produced. You'll see this is a relatively low product yield. Your recovery and purification of N-butanol from the fermented broth is also much more difficult and therefore more costly, because with an ethanol distillation process, you have a simple, relatively simple distillation process, because ethanol is removed at a temperature long before water boils. But the butanol actually boils at a temperature higher than water. There have been several research attempts to try and improve butanol production through evolutionary approaches and fermentation technologies such as gas stripping, which continuously removes butanol from the fermentation as it happens. There have been attempts to improve productivity in this way, so we can get final N-butanol concentrations reaching almost 30 grams per liter with these processes, but there's still a long way of going to produce enough butanol at a high enough rate and at a high enough yield to really compete even with bioethanol production. So improvements are required in yield, in sluggish fermentation, so we need to improve that fermentation rate. We need improvements, as mentioned, in end product inhibition, and as with any bacterial fermentation, a big problem is also bacteriophage infections. So we need strains that are not going to be attacked by specific bacteriophages. Alternatively, Saccharomyces cerevisiae and the bacterium Escherichia coli are also being engineered in order to produce isobutanol, which is comparable to N-butanol in terms of a lot of these positive qualities. But again, the production levels in those heterologous systems are not yet where they should be for industrial feasibility. Okay, let's look at biodiesel. We said that the transesterification of oil with an alcohol in the presence of a catalyst will produce a biodiesel as well as a glycerol. If your oil will most likely be from a triglyceride, and so glycerol is always going to be a byproduct in the process. It's an optimal way of creating biodiesel through this transesterification process, and depending on the alcohol used, biodiesel with different types of chemical composition can be formed. Using methanol for your transesterification, you get a methyl ester, and with ethanol, of course, you get an ethyl ester. Your catalyst can also be different types of catalyst. Alkali catalyzed transesterification is generally preferred as it is less corrosive, and people use sodium hydroxide or potassium hydroxide for this purpose. Although in some cases an acid hydrolysis, an acid catalyst is preferred if there's a higher water level in your oil. Enzymatic transesterification is also an option. This uses a lipase enzyme. This is being developed because it has quite low energy requirements. It also has overcomes issues such as difficulty in recovery and treatment of byproducts that requires complex processing equipment. And the drawback of this, though, is that the lipase enzymes are quite expensive, and you get relatively low yields and long reaction times, which makes it less competitive at industrial scale. There is quite a lot of research on using enzymatic transesterification, though. The idea is that you can perhaps put these enzymes in beads or on beads and design a process which can be continuous. And because of the specificity of the enzymes and the fact that you don't have to recover your catalyst, there is still a lot of advantages to this process overall, which is why it is still being researched. Then with biodiesel, the nature of the fatty acid has a big effect on the quality of the fuel. So the nature of the fatty acid has an effect on the characteristics of your biodiesel, and this affects the process that you have to use and how good your fuel is in the end. So most research on biodiesel production has concentrated on using feedstocks such as palm oil, soybean oil, sunflower oil, coconut oil, or rapeseed oil. Most biodiesel production at the moment is from waste soybean or from rapeseed or from palm oils. And as I said, if we want to move into that third generation biofuel, there's a lot of research on how best to transesterify those specific types of oils that you might have, which would of course be different from these plant-based oils. Okay, finally then, some concluding remarks for this article. I think it's clear that there's still a lot of research challenges for process optimization. The process of enzymatic hydrolysis of agricultural substrates still need to be improved. We need cheaper enzymes or enzymes with higher specific activity. We need to be able to handle a larger amount of solids in our fermentations, and we need these enzymes to be efficient at these higher solids loadings. We need the development of microbial strains that are robustly fermenting organisms that are tolerant to those inhibitors that I said are inevitable after pre-treatment that you will get in your hydrolysates. We need to be able to ferment all of the sugars available. It's no good having yeast that is very good at fermenting just glucose. We need organisms to be able to ferment those pentoses as well. We have to be able to have organisms that withstand high ethanol concentrations in the medium. So there are organisms that will use all of the sugars that are available in lignocellulosic biomass, but they can't withstand high ethanol production levels or high ethanol concentrations. We need to be able to produce depolymerizing enzymes more efficiently. So our celluloses, for example, we want to be able to produce cheaper, or we want our organism that is actually also going to do the fermentation to be able to produce its own depolymerizing enzymes. And then an optimal strategy for process integration, how to integrate all of these different elements is still required to reduce the number of steps involved and to be the most energy efficient. And then we need recycling, reduction, and reuse of all of the byproducts and the waste that is produced in the system as well, in order to reduce the energy demand and to be more to protect the environment. Okay, so that brings me to the end of this lecture, the end of this journal club. As I said, you will receive more instructions on the journal clubs that you have to do for this course. So I'm going to end this talk here.